All right, the moment you've all been waiting for. What do you need to know how to do from 5.2? First of all, the mean value theorem. Thing one, it must be a continuous function in the closed interval. Okay, well this is awful. Let me try that part again. In the closed interval. Thing two, it must be differentiable in the open interval. And if both these things are true, then there must be a value of c in that interval such that the instantaneous rate of change at c equals the average rate of change over the interval. Remember, failure to meet the requirements of the mean value theorem does not mean this isn't true. But if you meet these two requirements, then this is guaranteed to be true. All right, next, what else? Let's draw a picture of what the mean value theorem looks like. Here's some function. Here is the value. Excuse me, no, you know what? I don't like that. I want to change my function. Here is the interval. This is A. This is B. There is a secant line that runs between A and B. The slope of the secant line, the average rate of change of this function is f of B minus f of A divided by B minus A. If the function is continuous and differentiable, then there is some value C in the interval such that so bad at drawing lines. There we go. The instantaneous rate of change is equal to the average rate of change. Those two lines have the same slope. That is the mean value theorem. All right, increasing functions. Definition, increasing function, f prime of x greater than 0. Decreasing function, f prime of x less than 0. And one could modify this and say that in the interval it is increasing if at c the derivative is greater than 0, and it is decreasing if at c the derivative is less than 0. If two functions have the same derivative, then the functions differ by a constant. So if f prime of x equals g prime of x, then f of x equals g of x plus some constant value. Always plus a constant, plus a constant, plus a constant, plus a constant. Burn that into your brain. And I have one more thing, and I am out of Jamboard room, so I'm going to just go skip back and erase this since I'm not providing you with these anyway. You can always do a screenshot. Antiderivatives, and we are going to talk much more about antiderivatives in future chapters. If f, capital F of x, let me back up just a second. If the derivative of this function is equal to this function, then this function is an antiderivative of this function. Our examples that we have looked at is that since the derivative of v is equal to a, therefore v is an antiderivative of a. Since the derivative of position is velocity, then position is an antiderivative of velocity. And so it's just an easy way to think of it is that if you've got function, if the derivative gets you in one direction, then the antiderivative gets you in the other direction. All right, that is 5.2 in the calculus text. Thanks for watching. Hope you learned something, and we'll see you at 5.2.